In this R-Code tutorial, we're going to explore how to build and evaluate a linear regression model using separate training and testing data. First, we'll load the packages that we need for this task, including tidyverse and tidymodels. Throughout this tutorial, the data that we use will be the bike share data, and we'll store this as bikes, and we'll focus on just two columns within the bikes data, rides and temp. For a sample of days, rides for each day tells us how many people use the bike share service, and temp gives us the temperature in Fahrenheit on that day. Ultimately, our goal is going to be to assess how well a linear regression model of ridership versus temperature can predict ridership. Mainly if I know what the temperature is going to be tomorrow, or I have a forecast of the temperature for tomorrow, how can I use that to also predict how many people will use the bike share service? And the way that we're going to assess those predictions, or the quality of those predictions, is through a training and testing process. Now, there are various ways that we can do training and testing, but we're specifically in this video going to focus on the following. We'll randomly select 80% of our bike observations to train or build the model, and then we'll use the other 20% of our observations to test or evaluate the model. Now, notice here that I said we'll randomly select the training data, random being the key word here. So when we split the bike's data into training and testing sets, this is a random process. That's just to say, I'm not personally assigning which days get put into training and testing. I'm going to randomly sort the days into these two different training and testing sets. Now, whenever RStudio runs a random process, the results are determined by the underlying random number generating seed. But we want to ensure that when we have a random process, we're able to reproduce it. For example, when I knit my document, I want to be able to get the same results as the previous time I ran my document. I also want to be able to run my document, give it to somebody else, and have them get the same results that I get. I want reproducible results. And to ensure that a random process is reproducible, we must first set the random number generating seed using set.seed. Let's consider a simple example to explore the concept of setting the seed. In this example, suppose we just want to take a random sample of two observations from our bike's data. We can do so using the sample n function, and we indicate we want to take a sample from the bike's data of size equals 2. Now when I run this chunk, notice that I get a random sample of 2 dates. In those 2 dates, for one, the temperature was 95, and on the other, 55 degrees. Now if I run this chunk again, I'm going to get a different random sample. Here, the first one also happens to have a temperature of 95, and the second one has a temperature of 79. And I can run the chunk again and again, and notice that every time I run the chunk, I get a different sample of 2 dates. And that's great. That's what we want out of randomness, right? We're randomly selecting our sample. But again, we want to be able to also reproduce our sample so that our answers don't change every time we knit our document or run our code. And again, so that we can hand it off to somebody else and they can reproduce our work. To this end, we can set the random number generating seed. Here I've set the seed to an integer of 1. And this is arbitrary, and I'll talk about that for a minute. But notice that when I set the seed and then I take a sample and I run this chunk, I get a sample of 2 days, temperatures 64 and 79, and ridership values shown here. And notice that when I rerun the chunk, nothing changes. I get the exact same 2 dates from my data set. These 2 dates were randomly selected, but again, the reason that they're the same every time that I run this chunk is that the random process started from the same random number generating seed, here 1. Now the 1 is arbitrary. For example, maybe I use a seed of 2. And every time I run this chunk, the sample of 2 dates that I happen to get are different than the sample I got when the seed was 1, but they are the same every time I knit my chunk. Again, that's because underlying this random process, we're starting from the same random number generating seed. Okay, now that we've explored how set.seed works, let's randomly split our bikes data into training and testing sets. Again, we'll begin, since this is a random process, we'll begin by setting the seed. Within here, I can put any positive integer, or not really any. There is a max to the integer that I can put, but the max is so big that I've never hit it, and I have no idea what it is. All right, so we're going to use 253. And so I have my seed, and now I want to split my bike's data using a random process. The function that we use, or that we'll use in this class to get this 80% training and 20% testing split, is the initial split function. And I give the initial split function 3 arguments. First, I have to indicate what data set I'm starting with. So what is my complete original data? Here, bikes. I also have to indicate from that original data what proportion or prop do I want to be randomly selected for training. So I'll put 0.8 here. It has to be a number between 0 and 1, 0.8 meaning 80%. So I want 80% of my original bike's data to go into training. By default, the other 20% will go into testing. Now finally, notice here that I also want to ensure that my training and testing splits are similar with respect to ridership. Mainly, I want to make sure that I don't use, say, the days with the highest ridership to train or build my model, and then try to test that model using the days that had the lowest ridership. If I have that kind of skewed information about ridership in my training versus testing data, it's going to skew my model and therefore my predictions. So to make sure that my training and testing sets are similar with respect to ridership, or in general, my y variable, I can indicate that using this strata argument. So here I want to stratify my split using or according to the rides variable in the bikes data set. And finally, since we're running a random process here, I want to store the results. So I'll store this as bikes split. So now I can run this. And let's check out bikes split. Notice here that I'm given 3 pieces of information: training, testing, and total. The total number, or 731, that corresponds to the number of observations in my original bikes dataset. 731. And if I look at this number 583 that falls under training, and I think proportionally 583 out of 731, that's roughly 80%. In contrast, 148 will be roughly 20%. So what bikes split is storing here in the background is my complete bikes data, and each row has been assigned to training or testing. In total, there are 731 observations. 80% of these, or 583 days, will be devoted to training the model. The other 20%, or 148 days, will be devoted to testing my model. All right, so we have bikes split, which again includes information in the background about which days are going to be used for training and testing. But let's actually split it out so that we can build our models. Specifically, let's just get the training data from this split. So we'll start with bikes split. That's where the information is about what's training and testing. And then we'll apply the training function to that. And I'm going to store this, and then we'll look at it, but I'm going to call this bikes train. Basically, I want to distinguish the training set from the original bikes data. So bikes train, I took the split information, and I obtain just the training data. And now if we check out bikes train, we can look at how many rows it has. It's 583, just as we noticed above here. And I can check out the first, say, 6 rows. Right. So we see some information about the dates in our training set. Now we can do the same thing, except we want to get the testing data from this split. Similarly, we'll give this a name. We'll call it bikes test. And from the bikes split, to obtain the testing data set, instead of using the training function, we'll use the testing function. All right, so now let's check it out. The number of rows in our bikes testing data is 148. Again, if we go back up to our original split information, that was the number we observed here. And we can check out the first 6 rows. When I'm checking out the first 6 rows, mainly what I'm looking for here is just a confirmation that the observations that I have in my testing data set, notice here, right, they start with a temp of 49, then 53, that's different than the data that happened to be put into my training set. Again, some of the original data points are getting put into training and the others are put into testing, specifically 80% and 20% into training and testing. Okay, so now we have our training and testing data. We can use this now to build a training model. So again, remember that our ultimate goal is to build a regression model, linear regression model of ridership versus temperature. In tidy models, we'll take that 2-step process. Step 1 is model specification. And as usual, at this point of this semester, we have our LM spec, or the specification of our LM model. We want to do a linear regression model. In the regression mode, or it's a regression task, where our output variable ridership is quantitative, and we want to estimate this linear regression model using the LM function or engine. Now once we've specified our model, now we can estimate the model using our training data. So here I'm going to call this bike model train. That's what I'm going to store my training model as. As when estimating any model, I'm going to start with my model specification, and then I'm going to estimate or fit this model. And here I indicate that my specific relationship of interest is ridership versus temperature. And this is where I'm going to be careful. This is my training model. Again, I want to just build this model using my training data. So for the data, instead of giving it bikes, I'm going to use bikes train. Right. And we can run that and check out the basic coefficients. Again, the important thing here is that I'm building my model using the training data. That's the role it's playing here. Bikes train, its role is to train or build my model. Now, I want to evaluate how well does this training model perform on my testing data. Mainly if I use this training model to make predictions of ridership for my test data, how well do we do? All right, so let's just start by making predictions. If I want to make predictions of ridership for my test data, I have to start out by indicating which model do I want to use to make these predictions. Here we want to use our training model. Then we want to augment this model. And here, for augment, we want to augment our training model with new data, where that new data is the testing data. So I'm going to take my training model and make predictions for my test cases. Right? So the result here, what we see for each test case is the observed ridership, and then the training model prediction of that ridership, and the corresponding residual. So if I plugged the temperature value here of 49 into the training model, I would get this prediction, and that prediction of roughly 2,140 is roughly 911 less than the actual observed ridership on that test day. I can use augment to just pull some predictions from the model, but then if I want to evaluate how accurate are those predictions, we can calculate the mean absolute error of the residuals. Mainly we can calculate what's the average absolute residual or prediction error. For that, specifically to calculate the test MAE, again, we'll take our bike's model train. I must have named it something else, huh? Bike model train, singular. Okay, we can take our training model. Again, we're going to use that to make predictions, where the new data that we're making predictions for is the testing data. So this so far is the same code. That code will give us just predictions and residuals, and the MAE function is going to essentially summarize the residuals to give us the mean absolute residual or absolute error. Recall that with the MAE function, we need to provide two pieces of information. First, we have to indicate which column that we're piping into MAE indicates the true or observed outcome of interest. So here, the true observation is contained in the rides column, and we need to provide the column name for where the estimate or the model prediction is being stored. So again, if we look at that output from augmenting our training model, that prediction or estimate is stored in the .pred column. And running this, we get an MAE, a test MAE of roughly 1,154, meaning that when we take our training model, built using just 80% of the data, and we use it to make predictions of ridership for the other 20%, those predictions tend to be off by 1,154 riders.